Another example of the use of Ampere's law can be obtained in what I'll call the infinite sheet of current. And used to this was not done much, but now these devices are fairly common, and you see them uh, in a fair number of applications. I'm going to think of this as an infinite sheet. I really think of it as infinitely long, but in fact, I'm going to think of it more as a finite length. Current is traveling down this really a ribbon. In fact, you probably have seen these connectors. They're ribbon connectors, predominantly inside computers for power supplies and things of that nature, that deliver current to given locations in this sort of planar geometry. And the geometry it'll have a width W and a thickness T. And if you get on the end of it, all of these currents are coming right out at you. And I'll assume that we're somewhere near the center of this. There are some edge effects as you get to the edges, but use the right-hand rule, grab those wires, and by the symmetry, the magnetic field is in this direction on top and in this direction on bottom as you curl your fingers around and giving the direction of the magnetic field in both cases. And viewed again edge on, I'll choose a curve C to go around and apply Ampere's law to in this fashion. Again, it's probably somewhere near the center of it. Again, magnetic field on the top is going this direction, on the bottom is going this direction. The curve C is perpendicular to the plane of this sheet of current. And I'll say we have a total length L for this side here. Not the total width. The width would be from here to here, but only part of it. And I can get the current density for this whole sheet, really. Its current density, remember, is the current flowing down the wire times or divided by the area. And if I've got a total current I flowing in this direction, so I have I, and then the area that it's flowing through is just this total width here times the thickness of it, T, I've called it. So that's the current density. And now then I come back to this expression here. There's my curve C. Apply Ampere's law, B dot dl around this curve C is mu naught times the total current cutting through the area enclosed by the curve C. That's fairly easy to compute once I've got the current density. Because remember, current is current density times the area involved, and in our case, the current is only flowing through this thickness T, and it's only flowing through the width W, the part that cuts here. These are on the outside. If this total length is width, only the current through the length L, not through the whole width, cuts it. And so I have the current density, which is constant, times the area that the current is flowing through. Well, that's just T, the thickness, times the length L, which is the portion of the total width that it flows through. And then the other part is pretty easy. The two sides, the left side and the right side, well, the dl along here is perpendicular to the directions of the fields, and so the b dot dl vanishes on those. The only piece that exists is along the top, b dot dl there, and then coming back along the bottom, b dot dl here. But the magnetic fields are in the same direction, so I get b times L on this one, b times L on this one, since they're both going in the same direction. I get the current density, I over T times the total width, divided by the length, times the area, which is the thickness, times the length that the current flows through here. Those thicknesses will cancel. I'll get 2BL on this side, mu naught I WL, and then one of the L's cancels, and I get then that the strength of the magnetic field just outside this ribbon sheet conductor of current is mu naught I divided by 2W, the whole thickness, the whole width of it. So there is a magnetic field associated, and it is fairly constant for at least certainly near the center. And you have to be a little bit careful with these if you've got sensitive equipment or electronics that's close to these ribbon conductors and electrical devices, that you're not getting interference from the current that's going through these with whatever electrical device that might be just nearby, because they'll interact via the magnetic field. In any event, that's a magnetic field produced by one of these ribbon conductors that you see pretty commonly and as connecting power supplies and what have you in computers and electronic devices.